In the beginning, there was only darkness, not the darkness of an empty room or the hush before dawn, but a silence so dense, so absolute, that time itself seemed hesitant to pass. Think of a night sky, stripped of stars, stripped of even the hope of a glow on the horizon. This is where the story of black holes begins, not as monsters lurking in cosmic shadow, but as the most profound riddles ever posed by nature. To speak of black holes is to stand at the edge of what is known, peering into an abyss where the fabric of reality is torn, twisted, and rewritten. In this narrative, we will journey from the earliest whispers of their existence, through the fevered dreams of science fiction, and into the cold, dazzling equations of modern physics. Along the way, we'll confront questions that have haunted thinkers for generations. Could a black hole be a tunnel to a parallel world? A machine for traveling through time? A gateway to another universe altogether? These are not idle fantasies, but the very frontiers of human curiosity and mathematical audacity. Centuries ago, before the word black hole had ever been uttered, the seeds of these mysteries were sown. In 1784, the English natural philosopher John Michell imagined the existence of dark stars, bodies so massive and dense that not even light could escape their gravity. His calculations, eerily prescient, would be forgotten and then rediscovered in the age of Einstein. It was not until 1915 that Albert Einstein, with the publication of his general theory of relativity, provided the mathematical scaffolding for the modern concept of a black hole. Here, space and time became malleable, capable of being warped by mass and energy. Gravity was no longer a force, but an expression of the geometry of space-time itself. In 1916, the German physicist Karl Schwarzschild derived the first exact solution to Einstein's equations, a solution that described a point of infinite density, surrounded by an event horizon, a border beyond which nothing, not even light, could return. This was the singularity, a place where the known laws of physics collapse into meaninglessness. For decades, this solution was regarded as a mathematical curiosity, a freak of the equations, not a thing that could exist in the real universe. Yet as the 20th century advanced, the evidence began to pile up. In the hearts of dying stars, in the centers of galaxies, in the flickering X-ray emissions detected by telescopes, astronomers found clues that pointed, inexorably, to the reality of black holes. But as our understanding deepened, so too did the strangeness of these cosmic enigmas. The event horizon, once thought to be merely the boundary of no return, came to be seen as a kind of cosmic membrane, separating the known from the unknowable. What lay beyond? Could something or someone survive a journey into the heart of a black hole? Could these monsters be more than destroyers? Could they be portals, bridges, or even creators? The 1960s and 70s were a golden age of speculative physics. In 1963, Roy Kerr discovered a new solution to Einstein's equations, describing a rotating black hole, or Kerr black hole. Unlike the static Schwarzschild black hole, the Kerr solution possessed a ring-shaped singularity and an ergosphere, a region in which space itself was dragged around at dizzying speeds. The mathematics hinted at the possibility that such a black hole might not be an absolute dead end. Instead, it might contain a tunnel, a wormhole, through which a voyager could pass, emerging in another place, another time, or another universe. Science fiction seized on these ideas with glee. In the pages of novels and the flickering images of film, black holes became gateways to the fantastic, time machines, interstellar shortcuts, links to parallel worlds. Yet for physicists, the challenge was to separate fantasy from possibility. Could the equations of general relativity really permit such wonders? Or were they, like so many mathematical curiosities, doomed to collapse in the face of reality? To answer these questions, we must delve deeper into the mathematics and the paradoxes of black holes. At the heart of the matter lies the singularity, a point where gravity becomes infinite and space-time is crushed to zero volume. According to the classical theory, the singularity is shrouded by the event horizon, forever hidden from the outside universe. But the interior of a rotating or charged black hole, as revealed by the equations, does not always lead inexorably to destruction. In some models, the singularity forms a ring, and the geometry of space-time warps in such a way that a tunnel, A wormhole can, at least in theory, connect the interior to another region of space and time. This is the source of the Einstein-Rosen bridge, proposed in 1935 by Albert Einstein and Nathan Rosen. Their solution described a kind of tunnel linking two distant points in spacetime, a wormhole. But the bridge was unstable, collapsing too quickly for anything to pass through. Later, in the 1980s, Kip Thorne and Michael Morris explored the possibility of traversable wormholes, structures that might, with enough exotic matter to hold them open, allow safe passage from one universe to another. The mathematics is seductive, but the reality is harsh. The kind of matter required to stabilize a wormhole, so-called exotic matter with negative energy density, has never been observed in nature. Quantum theory allows for negative energy in certain circumstances, as in the Casimir effect, but not in the quantities or configurations required to prop open a wormhole throat wide enough for a spaceship, let alone a human traveler. Yet the questions refuse to die. In the 1970s, Stephen Hawking shattered the old certainties by showing that black holes are not entirely black. Through a subtle interplay of quantum fluctuations at the event horizon, black holes emit a faint glow, now called Hawking radiation, and slowly evaporate over eons. This discovery, elegant and terrifying, opened up new paradoxes. If information falls into a black hole and is then lost, does this violate the fundamental law of quantum mechanics, that information cannot be destroyed? Or does the information somehow leak out, encoded in the pattern of Hawking radiation, or preserved in some parallel branch of the universe? This is the black hole information paradox, and it remains one of the deepest mysteries in physics. It has led some theorists, like Leonard Susskind and Juan Maldacena, to propose radical solutions, that black holes are holograms, encoding the information of everything they consume on their two-dimensional surfaces, that spacetime itself is woven from quantum entanglement, that black holes might be linked, through the strange mathematics of ER-EPR, to wormholes formed by quantum entanglement. Here, the border between science and speculation blurs. The equations are precise, the mathematics rigorous, but the implications are so strange that they defy easy comprehension. Some physicists argue that the interior of a black hole may not even exist in any meaningful sense, that what we call the inside is a kind of mathematical illusion, a mirage conjured by the equations but inaccessible to experience or observation. And yet the dream persists. In 2019, the Event Horizon Telescope captured the first direct image of a black hole's shadow, a ring of fire encircling the abyss at the heart of the galaxy M87. This image, grainy but profound, was the culmination of decades of work by hundreds of scientists, weaving together signals from telescopes around the world. It was a portrait not just of a distant object, but of the limits of human knowledge, a glimpse into the heart of darkness, where the laws of physics are pushed to the breaking point. With every new discovery, the questions grow more urgent. Is the event horizon a one-way membrane, sealing off the secrets of the singularity forever? Or could it be, as some theorists suggest, a gateway, opening, under the right conditions, to realms beyond our universe? To explore these possibilities, let us examine the three great dreams that have haunted the science of black holes: portals to parallel realities, machines for time travel, and bridges to other universes. First, the notion of black holes as portals to parallel realities. This idea finds its roots in the mathematics of general relativity. The equations permit, in certain cases, the existence of multiple regions connected by wormholes. The famous maximally extended solution of the Schwarzschild metric, for example, contains not only our universe, but a mirror universe on the other side of the wormhole. However, this structure is unstable. Any attempt to traverse the wormhole would cause it to pinch off, trapping the traveler forever. Nevertheless, the mathematics is tantalizing. In the Kerr solution, the rotation of the black hole stretches the singularity into a ring, and the geometry inside permits paths, called geodesics, that loop around the ring and emerge elsewhere, or even in another universe. The equations suggest that, from certain vantage points, the singularity might be passable. A traveler could, in theory, avoid the region of infinite density and emerge unscathed in a parallel world. But these dreams are haunted by the specter of instability. The passage through the wormhole is beset by blue-shifted radiation, light and matter compressed to infinite energy, as the traveler approaches the singularity. The slightest perturbation, the tiniest ripple, causes the tunnel to collapse. In the real universe, with its chaos and noise, such perfect conditions are impossible. The wormhole closes, the portal is lost, and the traveler is destroyed. Next, the dream of time travel. Black holes, by their very nature, are machines for warping time. As one approaches the event horizon, time slows to a crawl, dilated by the fierce pull of gravity. To a distant observer, a falling object appears to freeze, never quite crossing the threshold. To the object itself, time proceeds normally, and the horizon is crossed in a finite instant. The mathematics of rotating black holes goes further. The Kerr metric admits the possibility of closed time-like curves, paths through space-time that return to their starting point, like a loop in time. In theory, a sufficiently advanced civilization could use such curves to travel to the past, creating paradoxes and causal loops. Yet nature seems to abhor such violations of causality. The physicist Roger Penrose, in his cosmic censorship conjecture, proposed that the laws of physics conspire to hide singularities behind horizons, preserving causality and the arrow of time. Stephen Hawking, in his chronology protection conjecture, argued that quantum effects would destroy any incipient time machine, preventing the formation of closed time-like curves. Still, the equations refused to be silenced. In the 1980s and 90s, Kip Thorne and his collaborators showed that, in principle, a traversable wormhole could be converted into a time machine by moving one mouth at relativistic speeds. The resulting temporal displacement would allow information, or even people, to travel into the past. But once again, the requirements are forbidding. Vast quantities of exotic matter, stability against perturbations, protection from catastrophic blue-shifted radiation. And so, the dream of time travel remains just that, a dream glimpsed in the equations but forever out of reach. Finally, the most audacious possibility of all, that black holes are bridges to other universes. In the multiverse models of modern cosmology, our universe may be only one bubble in an infinite sea of bubbles, each with its own laws and histories. Some theorists, such as Lee Smolin and André Linde, have speculated that black holes might serve as seeds for new universes, that the singularity at the heart of a black hole could bounce and give birth to a new cosmos, disconnected from our own. This idea arises naturally in certain models of quantum gravity, such as loop quantum gravity, where the classical singularity is replaced by a region of extreme curvature, a Planck star, from which a new universe might emerge. In this view, our own universe could be the offspring of a black hole in another universe. The chain of cosmic creation could stretch back without end. Yet this is, for now, pure speculation. The mathematics is suggestive, but the evidence is lacking. No experiment, no observation has yet confirmed the existence of parallel universes, wormholes, or cosmic bounces. The interior of a black hole remains forever hidden, shielded from our instruments by the event horizon. Nevertheless, the search continues. Physicists probe the edges of the possible, devising ever more ingenious experiments and thought experiments. They study the ripples of gravitational waves, the flicker of X-rays from accretion disks, the echoes of Hawking radiation. They map the shadows of black holes, parse the data from LIGO and Virgo, and build ever more sensitive telescopes to peer into the heart of darkness. In the laboratories of quantum gravity, where string theory, loop quantum gravity, and holographic duality vie for supremacy, the equations grow ever more intricate, ever more beautiful. The dream of unifying general relativity and quantum mechanics drives the search for a theory of everything, a single framework that can describe the dance of particles and the curvature of space-time. Amid these mathematical cathedrals, the ghosts of science fiction linger. The image of the black hole as a portal, dangerous, seductive, forbidden, continues to haunt the imagination. It is a symbol of the ultimate mystery, the place where knowledge ends and wonder begins. And so, the verdict of modern physics is both sobering and exhilarating. The equations of general relativity permit the existence of wormholes, time machines, and bridges to other universes, but only under conditions so extreme, so finely tuned, that they are unlikely ever to be realized in nature. The requirements for exotic matter, stability, and protection from catastrophic radiation appear to rule out traversable portals, at least with our current understanding. Yet the questions remain open. The paradoxes of black holes, information loss, holography, entanglement, point to deep truths about the nature of reality. In the interplay between general relativity and quantum mechanics, between the geometry of space-time and the probabilities of the quantum world, new possibilities may yet emerge. Perhaps, in some far future, armed with technologies and insights we cannot yet imagine, we will find a way to peer beyond the event horizon, to glimpse the secrets hidden within. Perhaps the portals of science fiction will become the highways of science fact. Or perhaps the true lesson of black holes is more subtle, that the universe is stranger, more intricate, and more beautiful than we can yet conceive. In the meantime, we are left with the poetry of the possible. Black holes, those silent sentinels at the edge of knowledge, beckon us onward. They remind us that every answer births new questions, that every horizon conceals a deeper mystery. In their darkness, we find the light of curiosity, the fire of imagination, and the endless hunger to know. To understand black holes as potential gateways, we must also grapple with the limits of observation. The event horizon, by definition, is a boundary beyond which information cannot escape. Everything that falls in, matter, light, even the patterns of quantum entanglement, is lost to the outside universe. Yet the mathematics of general relativity describes the inside of a black hole as a region where space-time is stretched and contorted in ways that defy ordinary experience. For a non-rotating Schwarzschild black hole, the interior is a one-way journey toward the singularity. Time and space swap roles. The singularity becomes not a place but a moment in the future, inevitable and inescapable. But in a rotating Kerr black hole, the geometry is richer. The ring singularity forms a gateway of sorts, and the equations permit paths that avoid destruction, at least mathematically. This leads to the possibility of white holes, the time reverse of black holes, objects that expel matter and cannot be entered from the outside. In the maximal extension of the Schwarzschild solution, a white hole connects to a black hole via a wormhole, creating a bridge between two universes. But white holes, like traversable wormholes, are unstable, vanishing at the slightest disturbance. Modern research has explored the notion of regular black holes, solutions to Einstein's equations, in which the singularity is replaced by a region of high but finite curvature. These models, such as the Bardeen black hole or the Hayward black hole, avoid the infinities of the classical singularity and may allow for new types of internal structure. Some theorists have speculated that such objects could harbor traversable wormholes or links to other universes. But the challenge remains formidable. The formation of a black hole in a collapsing star, as observed in supernovae and gamma-ray bursts, appears to result in a traditional event horizon and singularity. The extreme conditions required to create and stabilize a wormhole, or to engineer a white hole, are far beyond anything observed in nature. Quantum gravity, the as-yet unrealized theory that would unite general relativity and quantum mechanics, may hold the key. In loop quantum gravity, the singularity is replaced by a bounce, a region where quantum effects prevent the formation of infinite density. In string theory, the interior of a black hole may be described by a tangle of vibrating strings or branes, connected by higher dimensional wormholes. The ADS-CFT correspondence, discovered by Juan Maldacena in 1997, links the geometry of a black hole in a curved space, anti-de Sitter space, to a quantum field theory on its boundary. This holographic duality has provided new insights into the nature of black holes, suggesting that the information they consume is not lost, but encoded on their surfaces. The EREPR conjecture, proposed by Maldacena and Suskind in 2013, posits that entangled particles are connected by microscopic wormholes, Einstein-Rosen bridges, woven into the fabric of space-time itself. In this view, the universe is a network of connections, with black holes as nodes in a cosmic web of entanglement. Yet these ideas remain speculative, untested by experiment. The Planck scale, the realm where quantum gravity reigns, is far beyond the reach of current technology. The secrets of the event horizon, the fate of information, the possibility of parallel worlds, all are shrouded in mystery. Despite these obstacles, the quest continues. Gravitational wave observatories like LIGO and Virgo, have detected the mergers of black holes, confirming their existence and probing their properties. The Event Horizon Telescope has mapped the shadows of supermassive black holes, revealing the dance of matter at the brink of oblivion. Future missions, such as the Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, promise to open new windows on the universe, detecting the faint ripples of space-time from the most cataclysmic events. X-ray telescopes, like NASA's Chandra and the European Space Agency's Athena, peer into the accretion disks swirling around black holes, tracing the flow of matter and energy. In the crucible of theory and observation, new possibilities emerge. Some theorists have proposed that primordial black holes, formed in the earliest moments of the universe, could serve as windows into higher dimensions, relics of a pre-Big Bang era. Others explore the idea that black holes might be connected to the dark matter that pervades the cosmos, or to the mysterious dark energy driving the acceleration of the universe's expansion. The mathematics is intricate, the experiments daunting, but the spirit of inquiry is undaunted. Black holes are both the destroyers and the creators of worlds, the places where the laws of physics are tested to their limits. They are the crucibles in which new theories are forged, the touchstones by which our understanding of reality is measured. And so, we return to the questions that haunt the edge of knowledge. Are black holes portals to parallel realities? Could they be used for time travel? Are they bridges to other universes? Modern physics offers no definitive answers, only tantalizing hints and rigorous constraints. The equations permit the possibility of wormholes, time machines, and multiversal bridges, but only under conditions that appear fantastically unlikely. The need for exotic matter, the dangers of instability, the cataclysms of blue-shifted radiation, all conspire to keep the dream at bay. Yet the paradoxes of information, the mysteries of quantum gravity, the strange connections of entanglement, all suggest that the story is not yet complete. The universe may hold secrets more profound than we can yet imagine, waiting to be uncovered by the next generation of explorers. In the end, black holes are not merely objects in the sky. They are the limits of our understanding, the places where science meets poetry, where knowledge gives way to wonder. They are the portals not to other universes but to new ways of seeing, new ways of thinking, new dreams. In their darkness, we find the light of curiosity. In their silence, we hear the echoes of our own questions. And in their mystery, we glimpse the infinite possibilities of the cosmos. Let us then remember the words of John Archibald Wheeler, the great physicist who gave black holes their name. Behind it all is surely an idea so simple, so beautiful, that when we grasp it, in a decade, a century, or a millennium, we will all say to each other, "How could it have been otherwise?" Until that day, the story of black holes remains unfinished, a tale written in the language of mathematics and wonder, inscribed in the fabric of space and time, waiting to be told. As we drift further into the cosmic night, let us pause and consider the nature of the questions themselves. The desire to find portals, bridges, and shortcuts is as old as humanity. It is the yearning not merely to understand the universe, but to transcend its limits, to escape the prison of time, to leap across the gulfs of space, to connect with worlds beyond our own. Black holes embody both the promise and the peril of this desire. They are the ultimate test cases for the laws of physics, the places where our theories are stretched to the breaking point. They challenge us to think beyond the familiar, to dream of what might be possible if only we could master the secrets of gravity and quantum mechanics. The tension between possibility and impossibility is the engine of progress. Every advance in science has been driven by the refusal to accept the limits of the known, by the audacity to ask, "What if?" even in the face of skepticism and uncertainty. In the study of black holes, this spirit is alive and well. The equations are difficult, the paradox is profound, but the questions keep coming. Could a civilization, far more advanced than our own, find a way to stabilize a wormhole, to harness exotic matter, to shield itself from the ravages of blue-shifted radiation? Could the laws of physics themselves be different in other regions of the multiverse, permitting feats that are impossible here? Could the very structure of space-time be far richer and more malleable than we have yet imagined? Science fiction, for all its flights of fancy, serves a vital role in this process. It is the laboratory of the imagination, the place where new ideas are tested and refined, where the boundaries of the possible are stretched and sometimes broken. The image of the black hole as a portal, a time machine, a gateway to another universe, is not merely a fantasy. It is a call to explore, to question, to dream. The history of science is filled with moments when the impossible became possible, when yesterday's fantasy became today's fact. The discovery of quantum mechanics, the unveiling of relativity, the detection of gravitational waves, all were once thought beyond reach. Perhaps, in some distant future, the secrets of black holes will yield to our curiosity. Perhaps we will find a way to peer beyond the event horizon, to travel through the tunnels of space-time, to glimpse the worlds that lie beyond. Until then, we are left with the beauty of the unknown. Black holes are the cosmic mirrors in which we see our own ignorance reflected, the reminders that the universe is stranger and more wonderful than we can yet conceive. They are the sentinels of the possible, the guardians of the frontier, the keepers of the keys to reality itself. As we journey onward, let us carry with us the spirit of inquiry, the courage to ask the impossible question, the humility to accept the limits of our knowledge, and the wonder that comes from gazing into the abyss and finding, not despair, but hope. For in the darkness of the black hole, there is a promise, the promise that the universe is not yet finished, that new worlds await discovery, that the adventure of knowledge has only just begun. And so, let the story continue. Let the questions multiply. Let the dreams persist. For in the end, the greatest portal is not the black hole, but the human mind, the engine of curiosity, the forge of wonder, the birthplace of every new universe. And in that boundless expanse, anything is possible.